Welcome to the next lecture on pattern recognition. So, let us briefly recall what we have been doing so far. We looked at Bayes classifier and we seen that to implement Bayes classifier we need class conditional densities. So, we have been looking at methods for obtaining class conditional densities from the training samples of examples. As we see in last class, there are essentially two approaches to estimating densities given IID examples, parametric and non-parametric. Last class we saw that the parametric method, we assume the form of a density, that is we know the we assume that the density is known except for the value of some parameters, and then estimate the parameters from the training samples. We have seen many ways to rate different density, different estimates such as unbiased estimates, uniformly minimum variance unbiased estimates and so on. One property we looked at is consistency of an estimate. An estimate is said to be consistent if as sample size goes to infinity, it converges in probability to the true value of the parameter. And we have seen that maximum likelihood method is a general procedure for obtaining consistent estimators for parameters. Okay. We looked at the maximum likelihood method. In the maximum likelihood estimate, the estimate is defined as the maximizer of the likelihood function, and we have seen a few examples, but in any case in most standard density models one can analytically derive the maximum likelihood estimates. Last class we have seen it for a couple of examples. One is one dimensional Gaussian estimating both mean and variance, and we also seen a simple discrete random variable, namely the Bernoulli random variable that takes only two values 0 and 1, is like I toss a coin and find the probability of heads of a coin, estimate the probability of heads of a coin. For these two simple examples, we have seen how to obtain ML estimates. This class will see a few more examples of obtaining ML estimates and then close the part on maximum likelihood estimation of densities. Okay. So, we will start with a couple of examples. The first example, let us take the density to be exponential, that is where our feature value, which is a scalar here, has exponential density, that is the assumed density model. Lambda is the parameter and f x given lambda is lambda exponential minus lambda x. This is of course 0 for x less than 0. So, the lambda is the parameter theta here. Okay. So, we are given IID data, as I said we can represent data either by a boldface x or by the script d. This class will use script d. So, we are given n IID samples from this density, we do not know lambda and we need to estimate lambda given these IID examples. And for our estimation we have to maximize the likelihood. So, in this case the likelihood function is given by product I is equal to 1 to n of f x I given lambda, that is lambda exponential minus lambda x I. So, we want to find lambda, we are given x i's, that is the data, we need to find lambda that maximizes this. As I said last class, very often for ease of optimization, we take the log likelihood. So, if I take logarithm of this, then the product becomes sum, I get log of lambda plus log of this will become minus lambda x I. So, the log likelihood, which we normally denote by small l, once again that is a function of lambda given all the data, is this product becomes sum and ln lambda and minus lambda x I. So, sum I is equal to 1 to n ln lambda minus lambda x I. So, we need to maximize this with respect to lambda, right. So, for that we differentiate this with respect to lambda. The first term will give me 1 by lambda and there is the summation. So, there will be n such terms. So, I will get an n by lambda. The second term is minus lambda summation x I. If I differentiate that with respect to lambda, I get summation x I. So, differentiate with respect to lambda and equating to 0, I get this. Now, this I can solve, right. I take n by lambda on the other side and then we can solve for lambda. And if we solve, our final ML estimate, because in estimate I put a hat on top, is n by summation is equal to 1 to n x I, right. Once summation comes on that side, lambda goes there and n comes down. So, the final estimate is n by I is equal to n x I. This of course is intuitively very clear, because you know for the exponential density expectation, the mean is 1 by lambda, right. So, because a good estimate for mean is sample mean, a good estimate for lambda is 1 by sample mean. This is simply 1 by sample mean, right. 1 by n summation xi is sample mean. So, n by summation xi is 1 by sample mean, that is the Bayesian likelihood estimate for lambda. In general, if the parameters of the density are related to movements of the random variable and all movements of are expectations. So, if we take the corresponding sample mean approximations for the expectations, very often they turn out to be the maximum likelihood estimate for the parameters. We already seen this, for example, the maximum likelihood estimate for mean of a normal random variable happens to be its sample mean. Now, the maximum likelihood estimate of for lambda of a exponential density happens to be 1 by sample mean, because the actual mean is 1 by lambda. Okay. We will see a few more examples. So far we have seen only the scalar case for continuous random variables and one scalar case for discrete random variable. So, let us look at one vector case. Okay. So, let us look at a multidimensional Gaussian density. Here x is a vector, x is in d-dimensional real space, x is a d-component vector. This density is the d-dimensional Gaussian density. So, if x is x1 xn xd, then the joint density of all those features is given by this. Okay. I am assuming everybody has seen the multidimensional Gaussian density earlier. This is 1 by root of 2 pi to the power d into determinant of sigma exponential minus half x minus mu transpose sigma inverse x minus mu. As I said, our notation is that all vectors are column vectors. So, x minus mu is a column vector. So, x minus mu transpose sigma inverse x minus mu is a quadratic form which is scalar. Okay. So, here the unknown parameters theta are constituted by the mean vector mu and the matrix sigma. For this density, so if x a vector x has the above joint density, then this mu obviously because I am taking x minus mu, mu is also in RD, the d-dimensional vector mu is the mean vector of this mu, that is the expectation of that x will be mu, and the sigma is a d by d matrix which is the covariance matrix defined by this expect value of x minus mu transpose, because x minus mu is a column vector, x minus mu transpose is a d by d symmetric matrix. That this is the covariance matrix, and I suppose all of you know that the diagonal elements of the covariance matrix are the variances of the various components and the off diagonal elements are the covariances. Okay. And because this is a covariance matrix, is also positive definite, even though that fact does not concern us in this estimation. Okay. So, our job is given IID data from this density to estimate mu and sigma. So, to find ML estimate, we have to maximize the log likelihood. Once again, log likelihood is, the likelihood is product f x i given theta. So, log likelihood is sum f x i given theta, where d consists of the IID samples we have x1 to xn. So, if I substitute for this f x i right, into this expression, I am sorry about it, this is log. So, there is an ln here, the ln is missing, ln f x i given theta. So, if I take the log likelihood, I get summation I is equal to 1 to n. I have to take log of this. So, log of this will give me log of this term, that is minus half 2 pi to the power d into determinant of sigma. Log of this term will be simply minus half into that quadratic form. So, that gives me this as the log likelihood function. Summation is equal to 1 to n minus half ln 2 pi to the power d into determinant of sigma minus half x I minus mu transpose sigma inverse x I minus mu. Once again, mu and sigma constitute the parameters to be estimated. So, to get these estimates, I have to differentiate the log likelihood with respect to mu and sigma and equate it to 0, right. Now, mu is a vector, sigma is a matrix. So, to differentiate this respect to vector, that is, I have to find the gradient of this function with respect to mu. So, if I differentiate this with respect to mu, the first term is independent of mu. So, that will go to 0. The second term is a quadratic form in mu. So, its derivative will be simply sigma inverse times xi minus mu. So, if I differentiate like that, this is what I get. If I take derivative with respect to the vector mu and equate to 0, what I get is summation I is equal to 1 to n sigma inverse xi minus mu is equal to 0, right. The half does not matter because I am equating it to 0. The quadratic form's derivative is sigma inverse xi minus mu. So, that is how I get that. Now, I can solve this. The sigma matrix is non-singular, right. So, I can multiply both sides with sigma. So, that gives me summation I is equal to 1 to n xi minus mu is equal to 0. So, that gives me summation xi is equal to n times mu, or mu is 1 by n summation xi. So, that gives us our final ML estimate for mu as 1 by n summation is equal to 1 to n xi. Once again, even in the vector case, here of course, x's are vectors and mu is also a vector. So, even in the vector case, that is even for the multidimensional normal distribution, the ML estimate for mean is the sample mean. Now, what about the ML estimate for the sigma matrix? Now, that is a little more tricky because I have to differentiate this expression with respect to matrix. Okay. That is algebraically a little more involved. So, we will not do the details, but one can show that the ML estimate for sigma turns out to be 1 by n summation is equal to 1 to n xi minus mu hat and xi minus mu hat transpose. While all the algebra is skipped, I hope you can see that the final estimate is intuitively obvious. Why do you say intuitively obvious? We know how the sigma matrix is defined. For the given density, the sigma is nothing but expected value of x minus mu transpose. So, if you want to estimate it, I want to take sample mean of this expectation, that will be xi minus mu transpose summed over I is equal to 1 to n divided by 1 by n, but I do not know mu. So, I substitute mu hat. So, intuitively this is what we should expect the ML estimate for sigma to be, and it turns out to be that, even though because the algebra is rather involved, I have just skipped the algebra. So, let us look at one more example before we finish ML estimate. This time let us look at a discrete random variable again. We looked at a few continuous random variables. So, suppose you have a discrete random variable z. Now, this time let us not take any specific discrete random variable, any generic discrete random variable. Every discrete random variable takes, let us say is the discrete random variable taking only finitely many values. Let us say a1 to am are the values that the random variable takes, and the corresponding probabilities are p1 to pm. Okay. So, what is that we have to do? We are given data in the form of IID realizations of the z, and we want to estimate the parameters pi. Okay. Of course, the parameters pi have to satisfy. Pi define the mass probability mass function of z, pi's are probabilities. So, pi's have to be greater than or equal to 0, and summation pi is equal to 1 because summation of the mass function should be equal to 1. So, the parameters have to satisfy these extra constraints. Now, for deriving our ML estimate, we represent our random variable in a slightly different style. So, we will represent our discrete random variable z as an n dimensional vector random variable x. Instead of think of it as a scalar taking m different values, we think of it as a vector of m components. What is the idea? The idea is that if z takes the ith value, say ai, then we will represent it by x whose ith component is 1 and all others are 0. So, a z that takes value a is represented as a, so to say, ith coordinate vector in the m dimensional space. So, what it means is that the random variable x actually takes only m possible values, obviously because z can take only m possible values, and the values are 1 0 0 0 or 0 1 0 0 0, 0 0 1 0 0 0 and so on. Right? Each of the coordinate vectors are the only possible values for this vector x. So, we are going to represent values of z by this. This is nice because essentially in estimating p1 to pm, the actual values a1, a2, am do not make any difference to us, right. The values assumed by z are a1, a2, am. So, if a's are different, the actual data as we see it will be different, but the specific numerical values of a1, a2 do not make any difference to the probabilities. The probability say p1 is the probability of z taking its first value, say a1. Hence, this kind of representation allows us to look at ML estimate of parameters of the discrete random variables, any discrete random variables in a uniform framework. Okay. It is often called 1 of m representation for discrete random variable taking m values. So, there are a few things about this representation. Now, we are thinking of a random variable as a m component vector, and this representation satisfies the following. So, each value of z is a value of x. So, x is a m vector, but the m vector satisfies each component of the m vector is either 0 or 1, and some of the components is 1. So, these two together tell you that exactly one component is 1 and all others are 0. Okay. So, this is what our representation satisfies. Also, probability x I is equal to 1 is given by P I. When will the x superscript I be 1? X superscript I is the ith component of x. Ith component of x is 1 only if z has taken the ith value, namely a I, and the probability that z takes that value is P I. Yeah, just one clarification. You may be wondering why I am representing the components of a vector as superscripts. Normally, when we take components of vector, we represent a subscript. I can't represent them as subscripts because we already agreed that our data is x1, x2, xn, where x subscript 1, x subscript 2 is the representation for different data items, irrespective of whether x is scalar or vector. So, even for this vector x, the different IID data will be represented as x1, x2, and hence for components we are representing it as superscript. Okay. So, given this, now I can write the mass function of this vector random variable x as follows. F of x given p is my parameter vector consisting of p1, p2, pm, is product I is equal to 1 to m pi to the power xi. Because x takes only these values, x can take the possible values of x are x as an m component vector, the components being x superscript 1, x superscript m. Each of the components is either 0 or 1, and some of the components is 1, meaning exactly one component is 1, all others are 0. So, if x for example takes value 1 0 0 0, then f of x given p will be p1 to the power 1 and all others to the power 0. So, this is p1. So, that is exactly what is probability. This is a mass function. So, probability x is equal to 1 0 0 0 is p1, probability x is equal to 0 1 0 0 is p2 and so on. So, this is the right expression for the mass function of x. Okay. So, given this mass function of x and IID samples of x, we need to estimate the parameter vector p1 to pm. Okay. So, what is the problem now? For the problem of estimating the parameters pi is we are given IID data of x's. So, whatever z data we have, we can recode them into the corresponding samples x. Note that each xi here is a vector, right. So, each xi has m components. So, the first component of xi is xi superscript 1, the second component is xi superscript 2 and so on. So, xi is an m vector with each component being either 0 or 1, and for each I summed over j, xi superscript j is equal to 1 for all I. Okay. So, we are given data like this. This is the IID realizations of z on which we are estimating p's. We know the probability mass function of x, that is what we have written just now. This is the probability mass function of x, parameters by the parameter p. So, given the probability mass function of x, we need to derive the ML estimates for the parameters pi. So, what we have to do? Log likelihood function. So, what is my log likelihood function? L p given data is I is equal to 1 to n, L of f of xi given p. Now, xi given p is given by this, right. So, let us substitute that. So, that is ln of xi given p is product j is equal to 1 to m pj xij. Now, because of the ln, the inner product also becomes sum, right. So, my log likelihood now becomes I is equal to 1 to n, j is equal to 1 to m xij ln pj. So, this is my log likelihood as a function of p, and this is what I want to maximize to find my p's. Okay. So, we want to find the parameters, so values for pi to maximize the log likelihood L p given d. But we should understand that is not an ordinary maximization problem, it is not an unconstrained maximization. By unconstrained maximization, I mean I do not want to maximize this over all possible n tuples of real numbers p1, p2, pm, right. Why? Because we need to maximize my log likelihood over only those m tuples or numbers pi that satisfy this constraint, because this pi have to be a distribution. So, the maximization of log likelihood now is not an unconstrained maximization problem, but is a constrained maximization problem. So, the ML estimate now becomes a constrained optimization problem. What is the constrained optimization problem now? We want to maximize LP given D, which is given by this expression, subject to summation I is equal to 1 to m, pi is equal to 1. So, I hope all of you know about constrained optimization problems. So, constrained optimization comes as not simply maximize some function, but maximize some function subject to something, and because what we have is an equality constraint, we can do it using what is called Lagrange multipliers. So, we are going to solve this using Lagrange multipliers. There is just one point I want to draw your attention to. When we said this becomes a constrained optimization, we said pi has to satisfy two constraints, pi greater than or equal to 0 and summation pi is equal to 1. But when I formulated the constrained optimization problem, I have not explicitly included the non-negativity constraint. The reason is that it is easy to solve the constrained optimization problem if I have only equality constraints. Then Lagrange multiplier method always gives me exact analytical solution much more easily. So, what we can do is we can incorporate only this constraint, find what is the maximum. If that also satisfies non-negativity, we are done. Then we, even if we include the non-negativity constraint, would still have got the same solution. So, let us only put the summation I pi equal to 1 constraint and then solve it, and then we will verify that what we get also satisfies the non-negativity constraint. So, how do I solve the constraint optimization problem? How to find the Lagrangian? So, constraint optimization problem comes as maximize some objective function subject to some constraints. So, you form the Lagrangian by adding the constraint function, which here happens to be summation is equal to 1 to m pi minus 1. We have to add that to the objective function, right, with a Lagrange multiplier. So, that becomes the Lagrangian for this problem. This is the objective function, right. This is what we are trying to maximize, and this is the constraint function 1 minus summation pi is equal to 0, and lambda is the Lagrange multiplier. I have just changed the summation index from S to J, because we have been thinking of Pj's as the parameters, because this J and I are dummy indices, they are indices of the summation. So, that while differentiating we will not get confused, I have just changed the dummy index J to S in this expression. Okay. Now, what do you have to do? I have to take partial derivatives of this expression and equate it to 0. So, let us say I take partial derivative with respect to Pj for some j. So, the derivative goes inside the first summation is equal to 1 to n. In the second summation, only when s is equal to j is this expression a function of Pj, otherwise it is not a function of P subscript j. So, when I take the derivative of this the first term with respect to Pj, it becomes I is equal to 1 to n, and the derivative of this when s is equal to j, that will be xij by Pj. Right. So, my first term in the derivative will be xij by Pj, summation I is equal to 1 to n. What will the second term derivative? I have to differentiate this with respect to Pj, this is a constant. So, this is lambda times P1 plus lambda times P2 and so on. So, I differentiate with respect to Pj, I get lambda. So, when I equate the derivative to 0, I get summation I is equal to 1 to n, xij by Pj minus lambda equal to 0, j is equal to 1 to m. So, these are the all the j differentiating with respect to all the j's. So, I can solve this to get my Pj's as 1 by lambda summation I is equal to 1 to n xij. Of course, lambda is a Lagrange multiplier, I still do not know its value. I have to find the value of the Lagrange multiplier to complete my estimate. Okay. So, how do I get the value of Lagrange multiplier? By using my equality constraint. I have summation j Pj is equal to 1 as my constraint. So, if I sum this up, summation over j 1 by lambda summation I is equal to 1 to n xij should be equal to 1, then I can take lambda on that side. So, that constraint gives me lambda is equal to summation over j is equal to 1 to m, summation over I is equal to 1 to n xij. I hope this is clear. The constraint is you sum this expression over j, that becomes 1. So, then I am taking the lambda the other side to get this. Now, this is a double summation, both are finite summations. So, I can change the order of the summation. So, first sum with respect to I, then sum with respect to j. Now, that becomes equal to n. Why? In this inner summation, as you have seen, our xij's are such for in any vector xi, exactly one component is 1, all others are 0, right. So, this summation always gives me 1, and because of the outer summation I get n. So, the last step follows, because summation j is equal to 1 to m, xij is 1 for all I. Okay. So, this is the value of lambda. If I now plug in the value of lambda, I get my final ML estimate for Pj as 1 by n summation is equal to 1 xij. Here this has been quite an optimization problem. We had actually formulated the constraint optimization problem, use Lagrange multipliers and solve it. But at the end, what we get is very intuitively obvious expression. Pj is the probability with which the random variable takes jth value, right. If I sum I is equal to 1 to n xij, that sum will be exactly the number of times the jth value is taken. If jth value is taken, xij is 1, otherwise it is 0. So, the final estimate is the fraction of times the jth value occurs. The probability of the random variable taking the jth value is simply equal to the fraction of times the jth value occurs, right. It is no more than, if I want to estimate the probability of heads of a coin, then a good estimate is the fraction of heads out of n tosses, right. As a matter of fact, we have seen that that density in the last class, the Bernoulli density, there is a discrete random variable taking only 2 values 0 and 1. This is actually a generalization. This is a discrete random variable taking m different values, right. So, if I take m is equal to 2, this gives me the same thing as the Bernoulli random variable we considered last class. Only thing is, when m is equal to 2, I do not need to keep p1 and p2, because p1 plus p2 is equal to 1, any one of them will do. So, we will take probability of the first value as the parameter. When you have m, we keep the constraint that summation pi is equal to 1 and estimate all the pi. Okay. So, in that sense, this is a generalization of the binary Bernoulli random variables we have taken. Okay. So, let us sum up this example. This example is not just an example, it is actually much more than a simple example, because the distribution, that is the probability mass function of any discrete random variable that takes finitely many values, is simply specified by some m numbers pi, right. The numbers have to satisfy pi greater than or equal to 0, summation pi is equal to 1, except for that every discrete random variables mass function is simply specified by these parameters pi. Hence, what we just now got is a general procedure for estimating the distribution of any discrete random variable, right. Not one specific discrete random variable like Bernoulli or binomial or Poisson or any Poisson of course takes infinitely many values, but this is a general procedure for estimating the distribution of any discrete random variable. Okay. Also, when we consider discrete random variables, there is really no distinction between parametric and non-parametric ways of estimating, because a discrete random variable taking finitely many values, the most general distribution is still specified by m numbers. So, when I say I am estimating the m numbers, I am not constraining the random variables distribution in any way, right. In the continuous case, when I am assuming the density to be normal or exponential, it is an assumption, it is a restrictive assumption. The real data may or may not satisfy the assumption of the distribution that I have assumed. On the other hand, when I am estimating the distribution of a discrete random variable taking finitely many values, this procedure we just now laid out simply assume that the distribution is specified by m numbers p1, p2, pm, all of them are non-negative and they sum to 1, and that does not constrain the mass function of the discrete random variable in any way, which means what we have here is a way to estimate the probability mass function of any discrete random variable if you are given IID samples. Now, discrete random variables are also important in many pattern recognition problems, even though many pattern recognition problems also come with continuous random variables, but discrete random variable taking finitely many values are particularly important in some of the recent problems which are mostly web based, set and ranking, document classification, spam filtering and so on. For example, if I want to classify HTML pages as advertisement pages or information pages, ultimately the features I measure is the number of links it has, kinds of words it has and so on, right. So, the most of these features will take only finitely many values. So, for example, if I want to do document classification, what is a typical document classification problem? Let us say something like Google News, it gets feeds of lot of stories, news stories, and let us say it want to classify each story as entertainment, or it's a movie story, a sports story, politics, whatever. So, there are so many classes. Given the document, I want to say the document being a news story, I need to put a category to it. So, a very good feature vector is to ask for different words how many times the word occurs. So, if I get words like elections, constituency, Rajiv Gandhi or Rahul Gandhi, then I would think it is a political story. On the other hand, if I get words like balls, goals, kicks and so on, maybe it is a sports story and so on. So, as a matter of fact, this word count as a feature vector is very often used in document classification. It is called a bag of words representation. What we have is we choose some dictionary of words. So, some 1 to say 20,000 words, and then each document is represented by a 20,000 dimensional vector, where each component of the vector tells you how many times the corresponding word occurs in that document. Okay. So, which means each feature then would be a discrete random variable. Right. In such cases, each feature is a discrete random variable. The procedure that was just now given will tell you in all such problems, we know how to estimate the mass function of individual features, because we only considered a single discrete random variable. That means, you can get marginal distribution of each of the features in all such problems. Of course, to implement the Bayes classifier, we need the joint distribution of the feature vector, that is the class conditional density we want. So, very often what we will assume for simplicity is that features are independent. If we assume features are independent, the marginal distribution tells me everything, right. Then the joint mass function is simply the product of the marginal mass functions, right. As a matter of fact, this kind of a Bayes classifier, where the feature vector consists of number of features, each feature is a discrete random variable, then I estimate the marginal distribution of each of these features, right, just by the procedure that we just now outlined, and then assume that the joint mass function is simply the product of the marginals, and then use that as the class conditional density, right. Here I simply assume that different the covariance between different features is 0. A Bayes classifier implemented with such class conditional densities is often called the naive Bayes classifier. Okay. The connotation naive to say is that when I have, say, in the bag of words model, I may have 100,000 features. Now, estimating all the covariances is such a time consuming method, I simply neglect them. So, that is why it is called naive Bayes, and in many of search and retrieval, document classification and similar web based applications, a naive Bayes classifier performs quite well. As a matter of fact, for information retrieval people, naive Bayes classifier is a very important classifier. And the last example we considered in maximum likelihood estimation is how you can estimate the mass function of any of such discrete features which take only finitely many values. Okay. So, let us sum up what we have done about ML estimation so far. ML estimates of parameters of a density are obtained at the maximizers of the log likelihood function, right. Log likelihood function is simply the product of the density or mass function at the values of the data. So, I take the product and then either likelihood or the log likelihood I find the maximizers of the parameters, and that is my ML estimate. And once the ML estimate for parameters is given, now the class conditional density is completely known. Okay. We have seen many examples of how we can analytically derive ML estimate. We have seen one dimensional Gaussian density, we have seen multidimensional Gaussian density, we have seen simple examples of discrete random variables such as Bernoulli, simple examples of continuous random variables such as exponential, right. And we also seen how in general to estimate the mass function of any discrete random variable taking finitely many values, right. So, in all these cases we can analytically derive the ML estimates, And what is also interesting is the derived ML estimates are often intuitively very satisfying. See, very often in any density model, the parameters are related to movements of the density. All movements are some expectations, and we know from law of large numbers that sample means are good. Sample means understood in a generalized term or good approximations of expectations, and that is what turns and it turns out that all ML estimates are such sample means. For example, the actual mean of a normal density, the ML estimate for it is simply the sample mean. For an exponential density, the parameter is lambda, and lambda is related to the mean of the density by expected value of x is 1 by lambda, and hence ML estimate for lambda turns out to be 1 by sample mean, and so on, right. For the Bernoulli case, for the discrete random variable case, all ML estimates or the analytically are easy to analytically derive, and they always have some very simple way to understand them, right. So, ML estimates are easy to obtain for most standard densities, and this is a very useful method of estimation. Specifically, we have discussed how using discrete random variables, we can easily construct a so called naive Bayes classifier. Having said this, ML estimation does have its problems. Okay. Obviously, nothing is a solution for everything. The reason why we actually looked at ML estimate in the beginning is that we said ML estimate is a very nice general procedure for obtaining consistent estimators. What are consistent estimators? Estimates that converge to the true values as the sample size goes to infinity. Because these are consistent, if I have a large number of samples, I know I will get a good estimate, right, that is no problem. But what happens if I have small estimate, small sample size, right? The estimates can be quite bad. For example, let us say I am estimating probability of heads of a coin, and I do not have too much time. So, I will toss the coin only 3 times, and as my luck has it, all 3 times it turns out heads. Then if I want to take an ML estimate, I have to take it to be 1, nothing else. That is the ML estimate for probability of heads. ML estimate is the sample mean. We have seen the ML estimate for the Bernoulli random variable. Now, that is obviously not very good. I know that the coin is not biased to that extent, but I can do nothing, because for small sample size, that is how ML estimate turn out to be. What it means is, even if I have some knowledge about the possible values for the parameter, in this case I may know that the coin is not a two-headed coin, both probability of heads and tails are strictly greater than 0. But that of course, I do not know the actual probability of heads, but I know that the probability of heads as well as probability of tails has to be strictly greater than 0. But within the ML estimate, I have no way of incorporating this extra knowledge that I have, right. That is because the final estimated value is simply determined by the data. It is determined by the data alone and nothing else. If I got I tossed the coin 3 times and I got 3 heads, the maximum likelihood procedure does not leave me any other option but to say probability of heads is equal to 1. There is no way I can tell the estimation procedure that I know that the probability of heads is less than. This is another method of estimation that we are going to consider, because there are many other methods, but we will consider only 2 methods. So, the second method of estimation that we will consider in this course is called the Bayesian estimation. Okay, is also a parametric method. To some extent, this actually takes care of some of these problems with ML estimate. So, that it's for small sample sizes, this actually gives you better estimates. Okay. At the top level, the way I can distinguish between maximum likelihood and Bayesian estimation is, in the maximum likelihood estimation, the parameters are taken to be constants that are unknown, right. While I do not know the value of the parameter theta, theta is not random, theta is taken to be a constant. In the Bayesian estimation, we think of the parameter itself as a random variable. This is the basic difference between the Bayesian and maximum likelihood estimation. We think of the parameter itself as a random variable. Okay. Then, because we think of the parameter as a random variable, we say that our we are doing estimation because we do not know the knowledge of the parameter value. So, we capture our lack of knowledge about the value of parameters, that is the fact that the parameter can take different values, because we do not know what specific value it takes, even though we know the range of values it can take, right. So, we capture our lack of knowledge about the value of the parameter through a probability density over the parameter space. For all possible values that the parameter can take, we put a probability density function, okay, and we want this density function to capture whatever knowledge or lack of it that we have about the possible values that the parameter can take. Okay. Such a density is called prior density of the parameter. Prior in the sense, it is before I saw any data. Before seeing any data, I have some model, some density model for the parameter. Parameter is assumed a random variable, and this is the prior density, the density of the parameter before I saw any data. Any information that we have about the value of the parameter can be incorporated to this density model, right. Then we view the role of data as transforming our prior density, this is our view of what the parameter could take, into a posterior density, posterior meaning after seeing the data, right. So, we think of the role of data in estimation as transforming a prior density into a posterior density for parameters, okay. We will see many examples of that in the next class. By shortly I mean maybe next class, but in the rest of this class we look at just this viewpoint in a little more detail. Okay. We think of the prior density of the parameter as capturing what can be called subjective beliefs about the parameter value. Okay. The Bayesian approach is an approach to probability, not just about parameters. The approach is that one can capture through probabilities our subjective beliefs, right. That is why we are thinking of prior density of parameter as capturing our subjective beliefs about the parameter value. At this level, I will explain a little more presently, but what it would mean is our final inference about the parameter value is not completely governed by data alone as in ML estimate. The prior subjective beliefs I have about the parameter also play a role in making our final inference about the parameter value given the data. So, our final inference is not completely governed by the data alone, other knowledge we have also plays a role. This view is essentially an approach. So, let me put this again, our final inference is not completely governed by data alone, other knowledge also plays a role. This is an approach, not just though we consider only for parameter estimation, this is an approach to probability. The approach is characterized by thinking probabilities as also capturing subjective beliefs. We can broadly distinguish between what can be called a frequentist approach to probability versus what is called a Bayesian approach to probability. In a frequentist approach, we think of probability as a limiting value or the fraction of times an event occurs if I repeat a random experiment. There are a lot of things which we loosely talk in probabilistic terms, which are not really that kind of repeatable random experiments. We talk of probability that it rains tomorrow, because tomorrow but comes only once, I cannot in principle also repeat the experiment enough times. So, whatever probability I talk about, probability of rain tomorrow, is more like a subjective belief, of course, might be based on some data and some sound scientific principles, but it is still something that captures my belief and my ignorance about whether or not it rains tomorrow. So, the idea is that probabilities can also capture lack of knowledge through whatever subjective inference that we can make apart from only capturing situations of repeated random experiments. Yeah, maybe at this stage I can give you a classical example of Bayesian approach. I mean, this of course given by Bayesian statistician, so it is heavily tilted for the Bayesian approach, but still is an instructive example. Consider three situations of trying to make inference based on gathering data, based on making an experiment. Okay. The first situation is, there is a musician who says, if you just show me the notes, not the words, not the full score, but just a line of notes, of a song, I can tell you whether or not is composed by some famous music. Let us say whether or not is composed by Tyagaraja. So, we do some tests. So, we just write one line of notes, give to him. So, let us say in an experiment conducted 3 out of 3 times he correctly guessed whether or not what is given to him is composed by Tyagaraja. Now, situation 2, there is a lady who says if she tastes tea, she can tell you whether you poured decoction into a cup containing milk or milk into a cup containing decoction. Once again you conduct an experiment, 3 out of 3 times she guessed correctly. My third situation, there is a man, a drunk, who says when he is fully drunk, he can correctly predict whether a fair coin comes heads or tails. You conduct an experiment, let us assume once again 3 out of 3 times he guessed correctly. Now, what is the inference? If I go by data alone, like in the maximum likelihood, I have to either grant all 3 claims or not grant any of them, saying data is insufficient. But what most of us tend to do is that maybe grant the first claim, dismiss away the last claim as a lucky run, and shrug our shoulders about the middle, right, which is simply based on our subjective belief of what is possible and what is not possible. Of course, I took 3 to make it interesting. Let us say the experiment is 5 out of 5 times they guess correctly. Even then, we will certainly, when it becomes 5 out of 5, we are much more confident in granting the claim of the musician. We will still dismiss away the last claim as a lucky run. After all, there have been many cricket series where one captain always wins all the tosses. So, they can be lucky runs of 5 where you call a coin correctly, and we may still shrug our shoulders about the lady really had that ability or not. So, the idea is that data can speak only so much, right. There is also our subjective prior belief on the situation, which modulates our inference from the data. Of course, in this particular example, if I increase the data to 100, then I have to grant my third person is extra sensory perception, if it indeed so happens that he can correctly guess, right. So, the idea is that this our subjective belief can modulate what the data is trying to speak to us. Now, this is the basic Bayesian approach, right. So, we have, so in terms of the estimation of parameters, what it means is I have a prior subjective density over the parameters, and the data transforms my prior density into a posterior density. Okay. So, coming back, this will make sure that our final inference is not blindly only about data, but it also depends on the prior density. Okay. So, let us leave all the philosophy behind and come back to only the parameter estimation problem. So, as earlier, let theta be the parameters that we need to estimate and script d be the data. Data as usual is n IID realizations x1 to xn, the set of IID, and each xi has density f xi given theta. F x given theta is the assumed density model. Bayesian estimation is also a parametric estimation. So, there is an assumed density model f x given theta. So, x1, x2, xn are the data. So, what we have extra now is there is a prior density on theta. So, f theta is the density over the random variable theta. So, our theta is viewed as a random variable which has a prior density, we represent it by f, and the posterior density is the density of theta conditioned on d. After seeing d, my density becomes theta. Okay. So, now how do I get the posterior density? We use Bayes rule. So, using Bayes rule, I am assuming everybody knows Bayes rule for density functions, just like Bayes rule for probabilities. So, f of theta given d is given by f d given theta into f theta by normalizing factor integral f d given theta f theta d theta. The theta in the denominator, of course, is a dummy variable, because I am integrating with respect to it. I could as well have called it theta prime. So, the denominator is a constant. So, the posterior density f theta given d is proportional to the product of f d given theta into f theta. This is the Bayes rule. What is f d given theta? Because d is x1, x2, xn and they are IID, it is simply f of xi given theta. This is the data likelihood, right. So, the posterior density is given by the product of the prior and the likelihood function. Okay. As I said, in the expression, the denominator is not a function of theta. So, we remember that it is only a normalizing constant. So, whenever we do not need the real size expression, we simply replace by some constant, let us say capital Z. So, what happens is, even in maximum likelihood, we will calculate the likelihood function. There, we are simply asking which theta maximizes this. Instead of that, we are obtaining our prior density at that density which is proportional to the product of the likelihood, obtaining our posterior density at the density that is proportional to the product of the likelihood and the prior density. Okay. Of course, to make it a density, we need a normalizing constant that is given by this. Okay. So, we essentially given data on our model, because I know f x a given theta, I know how to calculate f d given theta, I am given a prior density. So, I take the product and turn it into density, that is my posterior density. So, in the Bayesian estimation, my posterior density is the final Bayesian estimate. Okay. We will see, of course, how do I find the posterior density and there are many other issues with it, but today's class will just look at the broad outlines. So, we take the posterior density at the final estimate. Then comes the problem, how do I calculate this? If this is some density over theta and I multiply this. So, for every given value of theta, maybe I can calculate this, but I cannot represent it as an infinite table, because theta is a continuous value, right. So, there is a problem of how do I represent the prior and posterior density, right. So, the important question, because we want to take posterior density at the final estimate, is how does one represent the prior and posterior densities. It would be nice if this can be represented in terms of parametric form. So, then we will simply store the corresponding parameter values for these densities. Okay. For that, what we would like is that the prior and posterior density should belong to the same parametric form. If the prior is say Gaussian density, we would like the posterior also to be a Gaussian density. Otherwise, every time I get more data, I may get a different density. So, this means I should choose my prior carefully. A form of the prior density that results in the same form of density for the posterior is called conjugate prior, right. A conjugate prior is a density for the prior that results in the same form of density for the posterior. Now, the posterior depends on the product of prior and the likelihood, and the form of likelihood depends on the form of the assumed model f x given theta. So, ultimately, what is a conjugate prior is determined by the assumed model and the data likelihood. So, for a given model and hence a given data likelihood, a different for a given thing, there will be some given density for p theta that becomes conjugate. So, if when we do Bayesian estimation, we will choose the right prior, so that it is a conjugate prior. We will see many examples of this next class, but the main issue here is when we use a conjugate prior, both prior and posterior belong to the same family of densities. So, prior might be some normal with mean mu 0 and variance sigma 0, and posterior will be also normal, only thing that may change is mean and variance. So, maybe mean sigma n and mean mu n and variance sigma n. So, then calculating the posterior is essentially updating the parameter density given the data and hence the data likelihood and the prior density, meaning give me mu 0 and sigma 0. Then the calculation simply involves how to calculate mu n and sigma n, namely the parameters of the posterior density, because we know prior and posterior will be the same family. This is what happens when we use conjugate prior, and the reason why when we do Bayesian parameter estimation, we always assume conjugate prior, but conjugate prior is not a single density. For a particular model, that is, when I am estimating mean of a Gaussian, something may be conjugate prior. When I am estimating a Bernoulli density, parameter of a Bernoulli density, some other density may be conjugate prior and so on. So, for each case, we have to find out what the right conjugate prior is. Okay. We shall see many examples on how this is done, that is when it becomes more clear. Okay. Now, you want to take the posterior as your final answer, that is the that is the end of the estimation. So, what does that mean? If I have the posterior density over theta, how can I use it in a classifier? Okay. My classifier actually needs class conditional densities, right. Ultimately, somebody has to give me class conditional density. So, that is the reason ML estimate gives me a particular value for theta. I plug in that theta in my model, that is my final class conditional density. But once we think of parameter as a random variable and have posterior densities, there is more than one possibility for this. Okay. One method is, can I use the posterior so that I finally get some density of x based on the data which is not dependent on any other unknown parameter. This is possible. Once I have the posterior density f theta given d, now I can write the density of x conditioned on d as density of x and joint density of x and theta conditioned on d, integrate this together. This is that I am obtaining the density of x by marginalizing over theta of the joint density of x and theta. Now, I can write the joint density as the product of conditionals. I can write this as x given f of x given theta d into f of theta given d, and x given theta d is same as x given theta, because I know once given theta, the data is not needed to find the density of x. The only thing unknown in the density of x is theta. So, if x given theta d becomes x given theta. So, this integral becomes integral f x given f of x given theta into f of theta given d theta. So, if I know the posterior, I know this model, I can integrate with respect to theta, I get something that is only dependent on data, right. Theta is now gone. So, this is what I can use actually as a class conditional density based on the data d. Of course, this may not always be possible. Only if this model is nice and if this prior density is nice, we may be able to crunch this integral to get this into a nice form that can be implemented. When it is possible, there is one way of using the Bayesian estimation for getting class conditional densities. Otherwise, we simply have to take some specific value of theta based on the posterior density. For that also there are multiple possibilities. One is we can take the mode of the posterior density, that is the value of theta at which p theta given d is maximum. Right, the posterior density is maximum, the value of theta that maximizes the posterior density is one value that I can take. This is often called the map estimate, maximum posteriori probability estimate. Okay. The map estimate is also something that is very specific only to Bayesian estimation, because it depends on the mode of the posterior density. So, it is actually the mode of the posterior density. Or we can simply take the mean of the posterior density as the parameter value. This is also possible. So, essentially looking at the posterior density, we take some specific value of theta obtained from the posterior density, add the final value of theta, plug that in and get our class conditional densities. All these are used. So, this is the general introduction to the Bayesian estimation. So, next class we will look at a few examples of how this whole thing is done, how in specific situations we get conjugate pairs, how we may be able to find f of x given d, how we may be able to find map or expectation of the posterior the estimates. We will once again do for the same densities, for normal density, for Bernoulli, for general finite value discrete random variables and so on. So, that we can compare the what the answers we get with ML estimation with the answers we get with Bayesian estimation. Thank you.